recording for a while. So okay, it's being recorded. So we have a equation called Schrodinger wave equation, and they solve that equation and plot the data in the three-dimensional form, and they get different kind of the solution. And I told you one is spherical, just like the golf ball, right? So they got something like this for something like this. They get something like this, just in x and y axis. So suppose this is a y axis and this is the x axis. So they just get something like this, like a dumbbell. So when you exercise, you have a dumbbell, right? So just like that. So they get something like this, and so they call this is one type, and then they call this is a px orbital. If they get the solution spherical like the golf ball, they say this is the S orbital. And if they solve the Schrodinger equation and they plot all those data and they get something like this, and they call this as the px orbital. This is I am in the first slide today. I already posted this slide, yeah. And then if some solution they get something like this. So all right, so this is x-axis, this is y-axis, and some of the solution they get something like this. See that? Something like this. So it's just like some of the solution come like the how you lift the dumbbell, and some of the solution come like the just you hold the dumbbell and just go like up and down, right? And then some of the solution they call this is a py orbital, and some of the solution they get something like this. X, this is the y-axis, and they hold the dumbbell like this. So like this. So they call this as a pz orbital. So these are the spaces where they find the electron. So suppose you have one electron in this this orbital, one electron, and this electron is jumping. Sometimes it is here, 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 sometimes it is jumping all around this space. See that? This is the probability of finding that electron there. But if you see here, there is no probability of finding electron in this space here. Right? See, it's almost not zero. So I'll talk about that. It's called the nodes, and I'll talk about that. So this is S orbital look like this, P orbital look like one of the P orbital look like this, and we call just like you hold like if you hold the dumbbell like this, that is a px. If you hold the dumbbell like this, that is a py. And if you hold the dumbbell like this, just between x and y, it that sphere looks the dumbbell like the pz orbital looks like this. So this is just the plotting of the data after solving the Schrodinger wave equation. And these are the spaces where you are going to find the electron. Suppose you have one electron, it is always jumping. This is jumping everywhere, like this. It's jumping everywhere. So at one moment, maybe it is here. Another moment, it is maybe here. Another moment, maybe it is here. So it is unlikely that it is it remains here. So this is the smallest where you hold your dumbbell. That place, electron doesn't want to sit there. Makes sense? This is close to nucleus. All right. So, and then these are the sp orbital. Now I'm going to talk about the SPD, so d orbital. So I have not talked the d orbital, and the d orbital looks like the double dumbbell. So I think I have a picture here. If you Google the shape of the d orbital, so you will easily get. Let's see if I have here. I think I have somewhere here. All right, so I have here one d xy orbital. So it looks like this. You see, different type of the d orbital. So they call dxy, dxz, dyz, and dz square. 1, 2, 3, 4. I think one more. I just forgot the name. That's okay. So it looks like this. So two dumbbells and try to bind them together when you hold it, right? So you see, it looks like so this is one dumbbell. So you are holding this dumbbell like this, and then pick another, and then hold like this. So so when you solve the Schrodinger wave equation, this gives many data, and once you plot those data, and this gives the sphere the space is like this. And suppose you have one electron. Suppose in this orbital you have one electron. That electron is something all the way. See, sometimes that electron is here, sometimes it's here, sometimes it's here, another time 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 it's here. Just jumping all along these spaces. Make sense? And these are the three-dimensional. It's not the plane. Yeah. So that's it. And now, so these are the orbitals, and let's talk about the size of the orbital. Size of the orbital is like this. So suppose this is the first orbit. This is here is a proton and neutron, right? Proton, neutron is the nucleus, and this is the first orbit. So the electron is here. So if you solve the Schrodinger equation for this first orbit, that is n is equals to 1, and the space you get S orbital is pretty small. So the sphere looks like pretty small. You see that? But if you solve the Schrodinger equation for the second orbit, this is n equals to 2, and you get the S orbital, and that S orbital for the second orbit looks to be big. As you go, as your number of the orbital, the size of the orbit increases, the solution of the Schrodinger wave equation is bigger value. So once you start to plot, it shows to be bigger size. Understand? Yeah? So just like this. So maybe you solve the Schrodinger equation for n is equal to 1. Maybe your S orbital looks like the golf ball. And then you solve the Schrodinger equation for the n equals to 2. Maybe it just become big like the volleyball or the football. You see that? Just like that. Yeah. So you get those points and plot those points and look how big it looks like. Yeah. So that's what it is. All right. Now, so let's talk a little bit about nodes and nodal surface and nodes. Nodal surface or surface, or they simply called nodes. Yeah? Nodes is a place. So nodes is a place where you don't find the electrons. So I already told you. So suppose we have a node here. Here. All right. So let's say let's take the p orbital. So I'm going to draw p orbital here. So this is x-axis, this is y-axis. So my px orbital looks like a dumbbell like this one, right? See that? Just like that. Now, along this surface, you see, it's just like this one. So this is the one side of the dumbbell. This is the another side of the dumbbell. And you're catching this dumbbell here, right? Just to lift it, right? Just like this. So this is the one side of the dumbbell. This is the another side of the dumbbell. And between this is a kind of this one, the surface. You see, between there is a surface, right? So along this surface, you can find the electron. So if you find the electron either this side or this side, but along this surface where I put the paper, there is no possibility of finding the electron, and that is called the node. Make sense? Yeah? So this side you find the electron, this side you find the electron, but along this where I put the paper and along this surface there is no possibility of the finding the electron, and that is called the nodal surface. So you see how many nodal? You see that? So along this where I put my hand here, along this one, along this surface, you cannot find the electron, and this is the node. Yeah? So that's called the nodal surface or the node. And how many node is possible there? There is a let's say this is I was talking about the px orbital. Now, if you talk about the py orbital, so this is going to be like this, right? So this is one part of the dumbbell. This is another part of the dumbbell. You will find the electron in this part and this part, but you don't find the electron in this part. So now I'm holding that dumbbell just like this. You see that? So this is the upper part of dumbbell. This is the lower part of the dumbbell, and along this paper where I put, you can't find the electron. So there is also that's the node. Make sense? Good. Now you do another way, and then you can hold the dumbbell like this. So this is This is y-axis, this is x-axis, and you solve the equation. I already draw along y and along x. Now I'm going to draw this along the z-axis here like this. So I'm just holding the boundary just like this. You see that? Just like this one, right? And then you have the electron in this side, you have the electron in this side, but along this surface, you don't have the possibility of the getting the electron. Along this paper surface, you don't have the possibility. So that's also nodal surface. So there is one nodal surface along here, and here is a one nodal surface here, and then in this one there is a nodal surface. So basically, I was holding this paper three ways. So one time I hold like this, and I said along the surface of the paper there is no possibility of finding electron. And another time I hold the paper like this, and then I say there is no possibility of the finding electron along this paper plane, right? And another way, I'm just holding this like this along the z-axis, and I'm saying that it looks like 30 or 50 degree, right? It's inclined. So along this surface, there is no possibility of the finding electron. Yes. It's like a plane. It's not a point. It's not a line. It's all the plane. So it's all the plane. That's why I'm just showing this paper, just like this paper. So all this plane, no possibility of the finding electron. Yeah. Yes. So that's how we interpreted these things. Yeah. So how many node is possible? So the number of you just go back and look what is the value of L. So L. So when we are talking about the quantum numbers, n cannot have zero, right? Which only start from n is equals to 1, n is equals to 2, n is equals to 3, right? We cannot say the orbit number 0 here because the 0 is not the orbit. Now, if you have a 1, and I told you the L value is just like n minus 1. How many values L can have is? So if you have n is equal to 1, we are talking about the first orbit, right? And when we say n equals to 1, we are talking about the first orbit. Now, that's 1 minus 1, that is 0. So L value has 0. You see that? That's how we calculate, right? So how many there is a 0. So L is equal to 0, and that 0 we give the name S, right? For 0 we give the name S, right? If you get the L is equals to 1, you give the name P. If L is equals to 2, you give the name D. S, S, P, D. And if you get L equals to 3, you give the name F, right? So that's how we name. Now, in the S orbital, how many nodes are there? 0. What is the number value? L, that is the number of nodes. So in S orbital, you find the node. So you have a here, and everywhere is a. Any question here? Just speak, yeah. So let's say you have a golf ball, just like the S orbital, just like the fist, and everywhere you can find the electron. Yeah. So there is no possibility of not finding electron anywhere in the S orbital. Make sense? P, you see now. Let's say n is equals to 2. I just something n equals to 2 here, and then L should be 0 and 1, right? Because the number of L should be n minus 1. So I have n2. So 2 minus 1 is up to 0 and 1 is equals to 2, right? So 0 to 1. So how many orbital I have? 0 and 1. So this is S, this is P. You see that? Now, with the S orbital, you don't have the nodal plane because this is value is 0. But for the P orbital, the value of P orbital is 1. So how many nodes you have for the P orbital? So this is a P orbital, and then told you. So along this line, you don't have the electron. So this is only one node, right? Just like you're holding like this, and then for the P orbital, you're holding like this, and there is only one plane, right? So, but if you talk, I'm just talking about the Px, but you talk about the Py, that's different. So Py is just like this, and there is along this line, there is no possibility of the finding electron, right? There is also one node. So all P orbital has one node, but S orbital don't have a node. Yes, so because the value of S is value of the s orbital is equal to 0. So 0 meaning that it doesn't have a node. What is the number of the value of that L? That is the number of the node you are going to have in that orbital. So now let's talk about the D. So L is equal to 0, 1, 2. So that is S, that is P, that is D. And if you have a 3, you are going to write the F, right? So how many orbital node is possible in D orbital? It's 2, right? You see how many S orbital has a 0 value, so node possible. In P orbital has 1 value, so there is only one node is possible. I already showed you by holding the paper, right? And then if you do the D orbital is a little complicated to visualize. So you need to take like this is one balloon, this is another balloon, and you make another balloon here, so like 4 balloons. And now along this line, you don't get electron. Along this line, you don't get electron. So you see that? So this is one surface, this is another surface. So D orbital there are two surfaces possible where you can find the electron. Make sense? So just think as a balloon. So you have a tie two balloon this way and tie two balloon this way. You have a now 2 orbital right there. So px or p. This is d orbital. So one is this way, another is this way. So along this line you can find electron. Along this one you can find the electron, but there is a space in between them. Just hold it, and you cannot find the electron. But along this line you can hold that paper, and in that plane you can find it. So d orbital has 2 possible nodes. You can find the electron. Makes sense? It's crazy, right? I don't know how they come something like this. All right. So now there's a table in I think the slide number 3. There is a table. So it's just now I think we already discussed those. I just want to practice a couple of things here. So let's say you have a n is equals to 1. How many orbital are possible? How many orbital are possible here? So L value is 0, right? 0. So that's the only possible orbital there. Yeah. Now you can easily see this one. If n is equals to whatever the number of square that one, and that is the number of all the quantum number possible. So let's say let's do some calculation here. Let's say n is equals to 1. So n is equals to 1. Now right, L is equals to, what is the possible value of L there? 0, right? 0. So 0. And then now write the possible value of ML here. So we need to go here. So that's 0 to 0. That's 0. You see that? And then so how many possible values here? So do they write MS? They don't write MS here. So you see, number of possible orbitals we have is just the 0, right? Just one. You see, so the number of possible orbital in any square. So you see here. So that's this number is any square value. So how many ml value we got here? Just the one, right? This is not 0. Maybe you are just reading this is a 0, but I'm saying that how many is this one? This is 1, right? N square is equals to 1. Now let's talk about the n is equals to 2. So I talk about the first orbit here. Now I talk about the orbit here. So how many possible values L can have here? So this can have 0 and 1, right? 0 and 1 values, right? Now how many ML values possible here? Now for 0, you are going to have 0. And then for 1, you are going to have -1, 0, and +1. You see that? Something like this. Now, how many are here? Now, you count all this. 1, 2, 3, 4. So, you see, now n equals to 2. Then you do the n square. That gives you number 4. 4 is possible. See that? So, if you have n equals to 3, now, what is the possible value of L? 0, 1 and 2. So you have to start from the 0 and go up to n minus 1. This is 3. 3 minus 1 is 2. So there is 3. So 0, 1, 2 is the possible value. Now start to do the, for this one, for 0 is 0. For 1, you are going to put like this. Minus 1, 0 and plus 1. You see that? And for this 2, you are going to put like this. Plus 2, sorry, minus 2, then minus 1, then comes to 0, then goes to plus 1, then goes to 2. You see, for this one, you got 0. For 1, you got minus 1 to plus 1. For 2, you got minus 2 plus 2. Right? That's how we calculate the, this is the magnetic quantum number. Now let's calculate how many possible here. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? You got 9, right? So when I was doing a 3, I got this value 9. So n square. So n is 3, 3 square is 9. You see that? So total number of orbital you can calculate from the principal quantum number n. So if you square that, how many possible the orbital you can find is like this. Yeah? Make sense? So what I am doing here is n equals to 1. So n is just 0, 1 value. So when n equals to 2, you have 2 values, 0 and 1. It cannot go up to 2. And when n equals to 3, that goes to 0, 1, 2. So all L values start from 0. What is the number goes up to that. And then ML values, at each L, it goes from minus that number to plus that number. So since 0 here, so 0 there. So for 0, there is no possibility of minus 1 plus 1. But I have 1 here. If L is 1, ML should be minus 1, 0 to plus 1. This one, right? And then when I was working here for third orbit, it was to 3. And so L possibility of L is 0, 1, and 2. And then for this 0, there is only one possible ML value. For this 1 here, then you have minus 1 to plus 1, minus 1, 0, plus 1. For this one, now you have minus 2, minus 1, 0, plus 1, and plus 2. So just count those all, and you have a 9 value. So how many orbital possible for any big orbit? So let's say, what I'm trying to here is, let's say I have this first orbit. So this is a neutron proton nucleus is here. I have just one orbit here. So how many sheets I can divide this into? How many sheets I can divide this orbit into? Just one. That because this is n is equal to 1, so n square is equal to just 1, right? So there is one sheet. I cannot cut that into many sheets to give many people. Just like that, yeah? Now I'm going to do n is equal to 2. So I have a bigger orbit here, n is equal to 2. So how many this n is equal to 2 I can divide into many sheets, and I can give one sheet like this for the individual person, right? So I just do like this, n square is equal to 2, 2 is equal to 4. So 2 square gives 4. So you see that the 4. So I can divide this n is equal to 2 or right into 4 smaller sheets, and I can give it 4 people. Make sense? Just like that. Crazy idea. Now, if I go to the n is equal to third orbit here, I have a big sheet, n equals to third, right? Now, how many sheets I can divide that third orbit into? N square is equal to 3 square is equal to 9. So I can cut this third orbit into 9 tiny sheets, and I can give it to the 9 people to sit there. People being the electron. Make sense? Just like that. So how many orbital is possible? How many this magnetic quantum number or the this number possible is can be calculated just by knowing the principal quantum number, and is by squaring it. Yeah. So that is what they are talking in slide number 3. Yeah? I think you practice it, and I think it will make sense. Now, if you have even bigger sheet here, n is equal to 4. Now, into how many sheets you can divide this fourth sheet? 4 square is 60. So you can cut that sheet into 16 small sheet, and you can put 16 to 32 people there. Sheet being two people. We will talk about that. So each of these sheets can have 2 electrons. So this 0 orbital can have 2 electrons. So this can have 2 electrons. Each of these sheets can have 2 2 people. Yeah. So you see, so that's how they come this idea. Right. So hopefully when you go home and you read a couple of times, it may make sense. So maybe it may not make sense now, but it is just think that if you have n is equals to 5, so this is a big one with 5. Now how many small sheet I can cut this into tiny the maximum possible uh, what you can cut this n is equal to 5 orbital is 5 orbit is equal to 25. I square is 25. So that fifth orbit can be cut into 25 tiny sheet like this, and each of those sheets will hold 2 electrons. See that? So you can put 50 electron there. Yeah? So a tiniest sheet in the atom can hold 2 electrons. Yeah? Alrighty. So here is one in slide number 4. So they're just talking about the s orbital, because if they start to talk about the p orbital, d orbital, f orbital, the things become so overwhelmingly complicated. So they cannot put something like that in the book. So they just give a very simplest orbital, that is the s orbital. So what is the shape of orbital? Of the s orbital we talk, that's a spherical, right? Like the golf ball. So this is the golf ball is just like this. So the shape of the orbital s orbital like this one. You see now. There's a plane, it's a circle, but it's not, it doesn't look like a circle, it should look like the ball, yeah, sphere. Yeah, so and then the electron is one electron, this is s orbital, and the electron is jumping around inside this this is jumping everywhere. You see that? It's jumping. Sometimes it's here, sometimes it is here, sometimes it is here. So that is one electron is jumping everywhere all the time. You see? So something like this. And then they calculated, is the electron always finding the probability of electron everywhere is same or not? They just calculated the probability. Will that electron stay more here in this region, or does that electron stay more in this region, or that electron just stay in this region? So they calculated somewhere where is will be this electron is spending most of this time during that jumping period. You see that? So just like this, I'm just dancing this way or this way or this way, but where is the possibility I'm spending most of the time while I'm teaching here? Most of the time I'm just sitting here, right? So maybe let's say there is a reference point somewhere, and then around that reference point, I'm just walking around that point, right? So they found that the electron doesn't spend equal amount of time in all the places. So what they found is something like this. So they plot the graph here, and they say, okay, this is the nucleus. So this is the nucleus here. This is the center of the ball, right? And then they plotted the data. So this is the probability of finding the electron, probability, where the probability, and they put here the distance. They put here the distance. So from this point, from this 0th point, whether that electron will spend most of the time here, most of the time here, or most of the time here, where is the place that electron is going to spend most of this time? Right? So they calculated and found this graph like this. So they found a graph like this, and then this goes like this. You see now, and then they measure the distance from the nut to this highest peak. This week you are doing some peak analysis in the Chem 106, something like that they did, and then this one. The distance of the nucleus, this is the high maximum probability, was found to be 52.9 picometer. So from this nucleus, the electron just try to spend most of its time in 52.9 picometer, maybe somewhere here, maybe somewhere here. This is the nucleus, and that electron, that one electron is jumping everywhere within the surface. But most of the time, we try to stay in this region where the distance from the nucleus to this region is, let's say, 52.9 picometer. So that electron most of the time spend its time around this region. Make sense? So from this one is a 52.9 picometer. Make sense? Now, what happens in the 18 picometer somewhere here? So maybe 18 picometer, from here to here is 18 picometer. So it spent its time there, but the time it doesn't spend much time there. You see that the probability is decreasing, right? And then how about if you come inside from that 52.9 picometer, let's say you come somewhere in the 10 picometer here. So you come here, so 10 picometer maybe somewhere 52, so maybe let's say 50 or 40 picometers, so somewhere here. So this is the distance. So you see, the probability of finding that electron doesn't stay much of the time near the nucleus. See that? What happens if you go to all the way to nucleus? It's a zero distance, right? From nucleus, so zero distance. How many times that electron is spending its time in the nucleus? Zero. Not spending. It's not coming to zero. Make sense? All right. So yeah, I think you go home and you read it, and it's yeah. So I only understood this concept when I started to teach. Yeah. So probably you understood something. All right. So there's a graph. So that's what. Yes.
Are you talking about the nodes?
No, I'm not talking about the nodes here. You can find the electron here. Find the electron here. Find the electron here. Find the electron here. You can find electron everywhere. So there is no possibility of that. What is the more probability? We are talking about the more probability. Make sense? Right? Interesting, right? Very interesting. I wish I could solve this equation and I could look myself what happens. All right. So I think we're good here. Now let's do some problem. I bring some of the problem here. So I'm in that slide number 7. So I just want to walk through some problem and what they expect you to know. Yeah. So number 1 in 7. What level is given to an orbital with the quantum number n is equals to 4? N is equals to 4 and n is equals to 1. So they are asking this question there in number 1. So where is the orbital? Where is the one? So you have a nucleus here, and then you have this is the first orbit, this is the second orbit, this is the third orbit, n is equal to third orbit, and n is equals to the fourth orbit. You see that? Where is the electron now? So that quantum number is saying your electron is in the fourth orbit. You see that? Now how many that fourth orbit can be divided into how many possible small shapes? And now we need to know, right? So since I have n equals to 4, now that orbit can be divided into 4 square is equals to, I can divide that number of orbitals, number of orbitals. Orbitals are orbital meaning the tiny space, yeah? So n is equals to, that's a big place, and we are dividing that into tiny space. See that? Tiny space. So how many spaces I can divide? I mean, how many sheets I can divide that? This big space that I can divide that into 16 possible orbitals. Make sense? That's what we practice, right? 16 possible. Now, among those 16, this is the one sheet. Level is 1. Make sense? There are 16 possible tiny sheets. Inside that n is equals to 4. Now they give one of the cities L is equals to 1. But there are 16 other 15 also, so they don't consider 15 here. Make sense? So what is this name? Now we need to give the name, and so we give the name as the 4, the principal quantum number. This is the 4, and then what is the, if L is equal to 1? What is the name? So you just look those how I wrote the name. If there is a S, this is 0. If this is a L is equals to 1, this is 0. This is a sorry. So I think if you have a 0, we give name S. If you have a 1, we give name P. If you have a 2, we give name P. If you have a F, we give name sorry. If 3 is for F, 2 is for D, 1 is for P, and S is 0. So that's how we name. Make sense? So what is the value of L here? 1. So 1 should be named as P, right? So S is 0, P is 1, D is 2, F is 3. So since I have L is equals to 1, so 1 is represented as P. So 4P. So when you have N equals to 4 and N equals to 1, the name of that one is P, 4P. Yeah? Good. Now, how if I have here 2 here? Suppose I have 2 here. 2 here. What will be the name? 4 is 4. This 4 is 4. Within 4, there are 16 seats. And out of those 16 seats, I'm just talking about one seat. And the name of that guy is D. 4D. Is it? Makes sense or no? I think it makes sense, right? It needs some practice. Yeah. Now let's talk about another question. So I already circled the 4p for. Now let's talk about the second one. How many orbitals are there in n is equals to 4? So how many orbitals possible is equal to n equals to 4? There is a big fourth circle, and I need to cut that into how many pieces? So that is n equals to n squared. That is 4 squared. So I can cut that big right into 16 small sheets, right? Simple. It's easy to memorize and like the systematically come and do the calculation, but intuitively what is going inside the atom, who knows, right? It's just a crazy idea. Alrighty, so now which quantum number or combination of quantum number is specified in given subcell of an atom? So how many quantum number we should know? We should know at least 2 quantum number. Yeah. So if you so the question was which quantum number or combination of quantum number is needed to specify given subcell in an atom. Subcell means big one, and then that big one can be cut into 16 sheets, and then we need to pick out of that one. So we just need 2 numbers, 4 and 2. See that? So we need to specify 2 numbers. One is a principal quantum number, another is a L value, azimuthal quantum number. Because how many possible L values there? There are 16 possible L values, right? So I'm going to put one guy in a particular sheet, something like that. Yeah. Now let's see 37. So let's look another one. Which of the following is not the correct representation of an orbital? Let's see. I was a little confused about that question, but I thought maybe they're doing something wrong, but not. So let's see 3s. So what is n value here? This is the principal quantum number. N is equals to 3. The electron is in the third orbit, right? And then third orbit can be cut into how many tiny spaces? 9 spaces. So now I need to go first L. So L values start from n equals to 3. We need to go up to 3 values. So the L value starts from 0. So 0, 1, 2. That's the possible of L values, right? And then if you want to go further, M values, the ML values are, so this 0 is 0. So this one would be -1, 0, +1. And then this 2 would be -2, -2, -1, 0, +1, and +2. You see that? That's how we got, right? So now let's see here. What is they are saying is 3f. 3s is possible. 3 is possible because this is in the third orbit. Do we have a s here? Definitely we have a s here. You see that? S is 0, right? So this is possible. S is possible, right? Good. Now because this is S, this is P, this is D. We give the name for the L. Yeah. Now let's start. So this is possible. 3s is possible. Is 3 possible or not? Let's see. 3 is 3. This is 3. Now there is a p orbital within this system or no? This is p. You can see here, right? Right? This is good.
Oh, that shit. I really just.
Any question there? All right. Now, what is that? 3D. Now let's look 3D. Is 3D possible or not? So this is possible, right? 3P is possible. 3S is possible. Now look 3D. Is it possible or not? N is 3 is possible. Now do we have a D somewhere here? Definitely D is here. So 3D is possible. Make sense? Good. Now let's look 3F. Now I'm going to look 3F. Is 3F possible or not? 3F. 3 is possible because the I is possible. Do I have a F here? I don't have a F here, so 3F is not possible. See, just look here, 3. And you need a 3 values here, and they start from the 0, 0, 1, 2. And 0 is S, 1 is P, and 2 is D, and there is no possibilities of Make sense? So 3F is clearly wrong. Did I make it clear? So you need to be able to look like, write like this one. And then, okay, 40, still we have some time here. So let's practice a couple of these here. Then, which of the following of the quantum numbers correctly represent the fourth orbital? So, we're doing the, yes, so number two, right? So 4p orbital. So 4p. So let's write 4p. 4p. So we are in the fourth orbit, and inside that fourth orbit, we are cutting that into 16 tiny part, right? 16 4 square. Now, what is the question? Which of the following set of quantum number is a 4p orbital? Now, m is equals to 4. This is the 4, right? Now write the L. So you see, when you have a 4 here, you need only 3 values here. So you start from 0. 0, 1, 2, 3. You cannot go up to 4. That's how they get number there. Now, then you see, now go to ML. That's a ML. So 0 have only 0 value. 1 has plus 1, sorry, minus 1, 0, plus 1. So I can divide it into like this. And then I can divide this into minus 2, minus 1, 0, plus 1, plus 2. So I'm just dividing each of the set into how many I can divide, yeah, according to the rule. And then I can divide this 3 into minus 3, minus 2, minus 1, 0, plus 3, plus 1, 2, plus 3. You see that? That will be possible, right? Now, you're just going to see the 4p. Now, let's look the first one, A. N is equals to 4. There is A. That's good. Now, do we have a L equals to 0? Do we have L equals to 0? Yes, I have L equals to 0 there. 4p, right? Yeah, I have L equals to 0. 0, what is the name? What is the name of 0? S? S, this is P, this is D, this is F. You see that? So that this is right there equals to 0. So I cannot write that there. That the one is clearly wrong. Right? Because it is asking, it is writing n equals to 4 and L equals to 0. And if L equals to 0, this is only possible, 4s. This is 4, S is 0, right? That's if it has a 4s, that would be good. But it is asking for P, so definitely that's wrong. L equal to 0 cannot have there, or 4p. Now let's look the P. N is equals to 4, L is equals to 1. You see, L is equals to 1 is P, right? This is equals to N is equals to 4. It's good. And it's giving the P. So we have 1 here, so P is good, right? So look the second number, L is equals to 1, which is good, right? So now ML is equal to 0. Now you see, do we have a 0 in ML? Many zeros are there. You see, here is 1 0, here is 1 0, here is 1 0, many 0 here. So this is good. Make sense? So for 4p, what are the possible quantum number? So n is equals to 4. That's L is equals to, you can have 1 because p is 1, right? S is 0, p is 1, d is 2, f is 3. And then since you have the L1, you have ML, many values from minus 1, 0, plus 1. You have also, so 4, 1, 0 is clearly is a matching number in B. Clear? That's how we practice, right? So just like that, you just keep practicing. And number 3, let's see how many nodal plane exist in 5D. So just the question is asking a little weird way. So how many possible nodes in 5D? So if it were S, no matter how many S. So if it were 5S, so we are just looking this one. How many nodes possible? That S has 0, right? This is a 0, so 0 node possible. Doesn't matter. We have 5 or 6 or 8 or 10. We don't. Doesn't matter. How many possible nodes in P? Doesn't matter. 5P, 6P, 8P. If you have a P, you have a 1 node, right? Because P has a 1 value. And D. So D is how many? What is the value D? L equals to 0, 1, 2. We give like that. So this is S, this is P, this is D. I told you what is the value over there. That is the number of nodes, right? So you see, if you have a D has a number 2 here, so D has a 2 nodal plane. I already told you. You have a dumbbell pointing one way here, another is pointing one way here, and cut in between. And there are 2 surfaces in the d orbital where you can find the electron. If it were a P, you just have one surface here. If the P was done like this, you have the surface here where you don't get it, just like that. So if you have a D, there is a 2 possible plane where you can find the electron. Make sense? All right, so like that. So let's see what I have here. So I put several questions from the book there. You just try practicing which one is possible, which one combination is not possible. I also put the answer and just think why something is possible and why something is not possible. Yeah. So just you try. So I'm just going to press one more and then let's see, in 38, the last slide, 38, explain briefly why each of the following is not possible set of quantum number. Let's look at A, last slide, number 8. So it's giving me n is equals to 2, L is equals to 2, and ML is equals to 0, and MS is equals to half. So this is good. MS I always should have, the last quantum number MS always should have plus half or minus half. If you see something else, that's clearly wrong. Yeah? So this is good. This is good. Probably this is also good. Now let's look here. So I have n equals to 2. I have n equals to 2. Now I'm going to write the L values here. So I don't look here. So don't look this part here. So I have n equals to 2. I'm just going to write how many possible L values for n equals to 2. That is 0 and 1, right? 0, 1. So I just need 2 values here. So 0 and 1. You see here, he's giving me 2. Is it possible? It's not possible. If you have n equals to 2, we just have 0 and 1. But he's saying he's giving us 2. So this is clearly wrong. Good. Now let's do another one. And so n is equals to 2, L cannot be 2. L only can be 0 and 1. If he has given 0, if you have given here 1, it is possible because 0 and 1, n equals to 2, and I have 1, it is possible. And I go further, and then this would be plus minus 1, 0, and plus 1. It's clearly 0 is possible, and MS would be good, right? Everything would be good. Make sense? Good. Now, let's do one more. There's a 1 minute time, and then so you are going to practice this. And so n is equals to, I'm looking the last one, n C, to a 38 C. N is equals to 3, n is equals to 1, ML is equals to minus 2, and MS is equals to plus half. You see? Good. This MS is plus half is good. If MS is plus half or minus half, this is good. Now I just don't look here, and I just try myself. So n is equals to 3. Now I'm going to write L. So for n is equal to 3, I'm going to write the values of L. That is 0, 1, and 2, right? It cannot go up to 3. So good. Then I'm going to write the L values now. For L values, for 0, I have only, sorry. For ML values, for 0, I have 0. For 1, I will have minus 1, 0, plus 1. You see that? For 2, I have minus 2, 0, sorry, minus 2, minus 1, 0, plus 1, plus 2. You see that? That's how I write, right? Now, it's giving ML is equal to it gives ML equals to minus 2. I think n is equals to 3, ML is equals to minus 2. But the ML is equals to minus 2. It looks right. I don't know where is the mistake here. N equals to 3, L is equals to 1, 0, 1, 2. It looks right. I think one time I wrote in right, and later I cancel, and I looked that one again. Yeah. So what happened here? So I think we should stop here. All right. So I looked at again what happened. So hopefully you learn something. It's not easy. Yeah. But you just try to count how we count those. All right, everyone. So thank you very much.